AI transcript, but
Yep.
and so yeah, it's recording that. It'd be good,
And
and then you don't really have to.
this is the mic. That's the mic.
Mic privacy is for remote participants, so you could block your mic from the remote participants, but that would block the mic in the room too.
Thank you.
Yeah.
So we'll just wait till 5 past. Yes. So if you don't have one, see me afterwards. Good morning. So it's 5 past, so we'll start. And I'm recording this one again because there's somebody who needs it, but I'm not sure that I'll record in future. Just some logistics. Most of the setup for the class now is complete. Canvas and Piazza are set up. All the labs and lecture notes are also in GitHub, and Canvas just points across to GitHub, so you should be able to get them there. This section is, we're going to go up from 32 to 40 students, although I notice we don't have 32 in the room at the moment. So that means we'll be getting a second TA. So between the two sections, we'll have 4 TAs. Now, both sections, this is section 1 on Wednesday, although I notice the university calls it section 4, but that's very confusing because there's only 2 sections. So we'll call this section 1. The Friday night section is doing exactly the same material, same labs, same assignments. So any TA should be able to answer questions on labs, for example. I've added a few more slides. I have marked them if what I've called bonus, and they will not be part of the quiz because we're doing the same quizzes and the same assignments, so it'd be unfair if we had them and they showed up in the quiz and the Friday people didn't have it. So I'll make that clear. There's some in this week, for example. I found PDFs of the other recommended readings. I've put them into Canvas, so you'll be able to get those. If they're O'Reilly, then you can go through OneSearch, which I know I put into Piazza, and you can get them there. So all of the books you can now get by PDF, because carrying them around can be quite heavy. This lecture is really today is when the course really starts. Last week was an introduction to scalability. Today, we're really going to cover material. Today's stuff is about doing concurrent programming in Java, and for that you will need a good IDE. I personally use IntelliJ. I go back and forth between using the community edition and the paid one. Personally, I think the community edition is good enough. Microsoft's VS Code is also a very good IDE. I mean, if you really want to use Vim and the command line, you can, but it'll be harder for you. For office hours, I've actually booked Crane next door, so there's a little bit of privacy, especially if you want to ask some question that you don't want everybody else to hear. But obviously, I will be here afterwards. And everybody should have received an invitation to AWS Academy. If you have not, you need to send email or ask on Piazza. Because that first lab is quite difficult setting stuff up. It's quite fiddly. But it's necessary. Now, another thing I promised that I would do last week is that I have put together a little 6-slide introduction to IP addresses, because I noticed that this class does not have networking as a prerequisite, and so some people have come in and don't know what I was talking about IP addresses last week, and I confused a few people because I was talking about public versus private IPs. So I've put together a tiny mini lecture, which I'll do at the end, just in case you don't know how that all works. It's certainly not a full networking course. Any questions before I go on? Okay. So this week is Java concurrency. So this is not so much about large-scale distribution, where you're distributing jobs between machines or between containers. I noticed that this course doesn't talk about containers, and I will do that. I'll add something to that later. This is about doing programming in the small using multiprocessing. Now, the course recommends this book, which is available on PDF. I personally learnt from this one many years ago. It amuses me that this one was written by Doug Lee, and he's still the last author on this one. In fact, I'd say if you're going to get a book on Java concurrent programming, it should have Doug Lee somewhere in the author list, because he really knows his stuff. But either one of these will be useful. Concurrent programming is a new skill. I'm not going to say that it's too difficult, but it is new. Yeah, so as I mentioned, I'm going to give a very brief introduction to actually that's to IP addresses, not all of TCP. I'll do that at the end. I'm hoping to have some time to walk through Lab 1 or answer questions. But as I said, we've got 3 TAs on Piazza who can answer your questions, at least one of whom I know has done the course last year. I've also thrown in a few slides to show how threads are implemented in hardware, because I personally find that it's nice to be able to understand where all this stuff's coming from. Like, I get threads, but how do they work? So the word thread comes from thread of control. That's why we use thread. Control meaning execution of a program. And the reason we've put concurrent programming into this course is because it teaches you a lot about stuff that's also relevant to distributed systems, because distributed systems are inherently concurrent because you have programs executing on different machines. They're obviously all executing in parallel. And so they can, the same issues that arise in concurrent programming in Java also arise in distributed systems. But it's easier to learn these skills and learn about the issues that come up programming in the small in Java. Particularly, you get this one. Events can happen on different nodes at the same time. Now, I remember when I was at University of Washington at IHME, I was looking at a shell script that somebody had written, and they had they had an if statement to guard something, and they weren't using locks. Now, I'll talk about locks later in the lecture, but it's what protects you. And I said, look, this is what happens if two programs get to this in the same point? And the person I was talking to, who was learning to be a software engineer, said, well, that's one chance in 1,000. I said, well, we run 1 million jobs a day. It's going to happen all the time, this problem. So the point is, on a large distributed system, or if you've got a lot of threads, things will happen at the same time. And unless you're careful, they will tread on each other's feet. If you try to write to the same file, you get smashes and things. You also can't predict the order in which things occur. Things will run slowly. You may think that, event A will happen before event B, but it might not. Now, on a web service, all web servers actually use threads. A good web server will hide the threading from you, and you just write your straight line code. But underneath, they're using threads. And you need that in order to be responsive to requests. Because a web server may handle like 100 or 1,000 simultaneous requests from people out there. And so what it will normally do is there'll be normally one control thread, a request comes in from a person, it will create a worker thread to handle that. And so you may have 100 separate threads, each holding one conversation with a user. That allows the server to handle many simultaneous requests. Now, I note that in the 90s, Sun Microsystems, the people who invented Java, they had a machine that had 64,000, could have 64,000 threads at one time, because it was designed specifically for web servers. If you're running a big e-commerce site, it could handle effectively 64,000 customers at one time. So that's actually the main slide. This one I added at the bottom. There's another reason you want threads. It's because threads are not just for web servers. If you're doing scientific computing, or if you're doing graphics, anywhere where you've got the same code but different data, then you have threads so you can subdivide the problem. This is called single instruction, multiple data. That's just an aside. Let me find that. Just if you're curious, I'd like a separate whiteboard, but I don't have one. Single instruction, multiple data. So, for example, a GPU works by having maybe 1,000 cores, and each core is working on a small part of the image, and each one of those cores is running one thread on a separate part. So that's another reason why you want to do threads. Right. So why do we do concurrency? As I said, it's a natural solution to many problems. To web servers, to scientific computing, where you say breaking down large matrix multiplication. There you can see little threads swimming through the Petri dish. There are other reasons the operating system may want it. Because if your program, for example, opens a file, then it's going to have to wait for the disk access or RAM access, or perhaps you're reading over a network, and so it's quite a fair bit of time. So the kernel, the operating system, will pause your process, take it out of the run queue, and let something else run while that's happening. In particular, all modern CPUs are multi-core, and I've got some pictures of them later. But this Yeah, the image is a bit rough, but so with a multi-core processor, when we first started, we would have a CPU had one core. It had one arithmetic logic unit that could do addition and subtraction. If you're lucky, it did multiplication, and one set of memory. And these would get faster about every 18 months. They would get twice as fast. But unfortunately, to get fast, you have to shrink the silicon, and we've reached fundamental limits on how small we can make the wires in silicon. These days, we have to use ultraviolet light, for example, to do the masking, not visible light. The wires are only 100 atoms wide, and you start to get quantum effects, and it just doesn't work. We can't shrink it. So the way we can't make them run faster, but what we can do is we can put more cores onto one piece of silicon. And so so if you're going to use a modern processor, you have to be multi-threaded. If you've got questions, please ask at any time, because you're all quiet, I've got no idea what you're thinking. Yes. Yeah, so the question was, can one core only do one thread? Yes. Now, 2 years ago, probably 5 years ago, the Intel chips used to run 2 threads on one core. But there's some very interesting security problems that are caused by that, because if you have a malicious thread running a bad actor running with a good actor, the bad actor can have some access through. That was the Spectre meltdown attack, which is well beyond this course. But there was a side channel attack called Spectre meltdown that is why we no longer run more than one thread on one core. So this is a bonus slide because I think it's important to understand where it's coming from. So a basic CPU looks like this. It's got the arithmetic logic unit that does arithmetic, addition, subtraction, maybe multiplication. Division is really hard, so often they don't do that. Program counter to keep track of where your program is up to, which is the next instruction. What is the next instruction? I'll ignore that. And memory. And then it has fast registers that the ALU can use when it's doing its actual. Think of that as a scratch pad. Or as my grandfather had in elementary school, it's a slate where he's writing on it. And that's a simple CPU. I'll come over this side, sorry. This is a simple CPU from, say, the 80s, or if you might find it in something like a coffee machine now, where you don't need a lot of compute. And so here you can see the ALU, the arithmetic logic unit, carry. When you add 2 numbers and you add a 6 and a 7, that gets to 13, you have to carry 1. Well, of course, it's in binary, it's different, but the carry logic is complicated, and that's what it looks like. But it doesn't look like that anymore. Now they look like this. Well, actually, they don't look like this. This is still a few years old. I had a look at the Apple M3 silicon, which is what you would find on a laptop, and they're even more different. Here you can see the repetition of the 4 cores across. And yes, question. Oh yeah, very good question. What are the drawbacks of concurrency? That comes. It comes in a few slides. Programming is harder because things happen at the same time. You have to be very careful that you don't come up with what are called race conditions, where 2 people are trying to update things at the same time, or deadlocks, and that's a lot of the subject of this lecture. So, but yeah, it's harder, no question. Anyway, that was just if you were interested in how these things actually work. So you don't have to know about hardware, but I would personally like to know what's running my stuff. Now, this one's important. Threads versus processors. So if you're on a Linux machine, like when you're on AWS and you get across to there, or if you're on a Mac and you go into the terminal and you run the PS command, that will show you processes. A process, and in the old days, that's all we had. It was a process, and it has the code you're executing. It's its own set of registers, like I showed you a couple of things, and the stack. When you call one function to another, one method to another, then you get stack frames. But when you go to multi-threaded, you have the process has one set of code, but then it has one set of registers and stack per thread. Big difference is that all these threads share the same address space, the same memory. So the threads can easily pass information from one thread to another. But to echo the question from the back, that also means they can accidentally smash the memory belonging to the other thread and cause problems. So the sharing brings you efficiency. It also brings you things you have to care about. The process also carries all of the permissions. And when the operating system starts a process, it starts it as a particular user with a particular set of permissions. With the thread, so this process, if I start that, it would all be under my gfips user with all exactly the same permissions. All these share exactly the same thing. So they're lighter weight from an operating system point of view. Yeah. Within the same process, all threads can see all memory. So each thread, so no threads do not have, well, go on. No, actually, they can. Each thread can see all of the other memory. Now, there is a caveat when we get to talk about Java threads. The Java virtual machine will give each thread a personal set of memory. But if you were writing a raw assembler, no, there is no separate memory per thread, except for the registers and the stack. We come back. Because each thread is running on its own, so it has to have its own set of stack frames. But the heap is shared, for example. I've covered a lot of this. Yep. So processors, virtual address space, meaning memory. They each have their own memory. So I'm going to ignore the fact that there are operating system calls that allow you to share memory between processors. That's an advanced topic. We're not going to do that. In general, processors have their own memory. They have their own set of code. They have their own security context. They have their own environment variables. Lab 1 used environment variables in a couple of places, particularly for the version of Java, I think it was. They have their own set of handles to system objects like sockets or database connections, and one thread of execution. Right. Yeah, I just want to emphasize the stack space. Because each thread is running independently and calling its own functions, it has to have its own stack. Actually, when I use the word stack for a program execution, is that something you're familiar with, or because I've learned it in compilers, and I know you don't tend to do compilers here. Somebody explain to me when I'm using the word stack, what does that mean? I know what you mean. But I am going to take a little bit of time just to draw it because, sorry, I realize I'm tending to go this side because I'm right-handed. My apologies. If you've got a function and it calls G and then G calls H, traditionally stacks are drawn up, but they usually go down. And so if they've got local variables, there will be a stack frame for that call for F and its local variables, and then a stack for G, and maybe it's got some local variables, and then a stack for H. And that's how, in a good programming language, each function has its own local variables and can't accidentally access the other ones. I said good because in C you can actually do that, but that's function call. Yes, is a very big difference between function call and function definition, but I can't go too far into that because this isn't a programming language course. Okay. And yeah, the cost of intercommunication is much lower between threads because they all share the same memory, same security. If you want to have one process send a message to another process, then the operating system gets involved and will check whether you've got security, has to create a place to store that information. Okay. How are we going for time? Good. Now this course uses Java. I wanted to talk about why. The big reason is because Java, right from the beginning, was designed with threads in mind. I was actually at Sun Microsystem when Java was designed. I was in a programming language project. We were going to replace C++ with something better. After a little while, we learned that there was another project inside Sun to create a programming language that would replace C++. That other project was Java. My manager was offered to join with the Java program. He said no. And as a result, I am not famous because I was not part of the original Java team. But it's critical that Java was designed right from the beginning with threads, because threads, for example, change the way the compiler has to work. It's critical. So that's why we're choosing Java. You can do threading in C++, but C++ is already a hard language. I don't know whether you guys learnt C and C++. Yeah, it's so you know what a core dump is and memory smashes. Yeah, you don't want to deal with that. It's just too hard. We'd spend more time debugging C++ than we would. Python is much easier than Java, but unfortunately it was not built with multiprocessing in the beginning. If you know Python, you would know probably that there are multiprocessing packages, but it's not built in. The global interpreter lock means you effectively can't do concurrency. The only way to do threading is to write a C++ plugin. So we're not going to do that. We could have used Go, but then you'd have to learn a new language, and that would just throw more into the course. So let's not do that. Now, all the code in this lecture is in the Git repo in a subdirectory called sample code. So you can do that. I am now going to switch to my IDE because there is code on the screen, but now this is tricky because now I've only got one screen here. So simple threads, naming thread and the runnable. Okay. I personally prefer to see it in the IDE. So yep, good. So I'm using IntelliJ Community Edition here. And let's go to this one. I'm just going to go back to the slides and check. As I said, this code is in the GitHub, so you don't have to copy it down, but it just looks better. And what I'm doing here is looking. I will actually, let's just copy this out. Is this the one? No, not that one, that one. Yeah, for some reason. Sorry, I've just gone quiet because I can't talk and code at the same time. This might. So get this in. This might be too much to try to do it right during a class. Yep. This should be in a main function. I'm not going to sit here in front of you and do a main function. But so there are two fundamental classes you have to know, or one class and one interface. I'm just looking for it in Java that you have to know about. One of them is runnable and the other is thread. A thread actually gives you access to the thread of control, gives you a core. And here you can see we're creating a new class called myThread, which extends thread. Thread is a class, not an interface, and instantiation, and then the start method is what actually starts it, and that program, this thread will now run, and it will print that out. There's a slightly more complicated example, which I'll actually run in the IDE. Sorry, I also don't know, do you guys know Java? Bon. Good, okay. We'll now look at this other one, which is called simple thread example, which I think is a little bit of a stretch because it's a bit more complicated. So in this case, we're going to use this class called naming thread. And what the naming thread actually implements runnable. Now, the runnable so Oracle, Sun Microsystems, you probably know all this. Sun Microsystems invented Java, Oracle bought it. If you want to get the canonical documentation, that's where you go to. So there's runnable, for example. It has exactly one method called run, which just means do it. So if we look at the naming thread, it implements runnable, so it must override run, and all it's doing, this is a hello world program, so all this runnable is doing is printing out a message. Now I want to show you a bit about programming. Let me just close a few windows here. So here we're going to use it. So we're actually going to create 3 threads. So we're going to create 3 naming threads, 0, 1, and 2. And then we're going to create 3 more threads. Zoom in, right? Can I zoom in? Yes, I can. It's also in the slides, but I prefer the colors. I'm about to comment on a programming style here, because I went and read this example and I thought, just a minute, it says we're creating 3 threads and here we're creating 6. And I thought, this is wrong. Why did Ian do this? And so then we go back and look at this, the naming thread. Notice I'm using Command B to switch between. Now have a look. Naming thread implements runnable. So it's not a thread, it's a runnable. And by choosing a bad name, he confused me, the person who came in later to look at this code. One of the things I'd always tell people when I was training my engineers is names are important. If you choose a bad name for a variable or a class, you will confuse the next person to read the code. It's either going to be a person who has to maintain your code, or it could be yourself in 6 months because you can't remember what it was you did. So I'm actually going to change it. And then we go back and we go to the simple thread example. And now you can see it makes more sense. We're going to create 3 runnables. And then for these runnables, the first thread takes that runnable, the second thread takes that runnable, and like that. Of course, we could have nested the constructor inside the thread, but let's not do it. Now we're going to start. And the start method for the thread will now call the run method on each of these objects, because threads are objects. And we're going to wait a little bit and then see. So now I can, with a little bit of luck, if I run this. Okay, let's get rid of that. Let's just delete that class because it's going to try to compile everything. Yep, okay. So here you can see, if we look back at naming runnable, I'm just going to, in the constructor, it just has a little method, just says I've been called. So you can see here, the constructors are called. And then in the run method down here, it just prints out that it's run. Not very exciting, but this is your hello world. I'm not quite sure. Is this really basic? Do you want me to go faster? Yeah, I'll speed up. Let me see what's next. Right. waiting for threads to terminate. Now that one is in join threads. So the first one just kicked off the first example, the naming runnable one, just set the three threads running, and when they and then the main program, the main thread exited. Well, didn't wait. You can wait for threads to join, and this is very, very common. I just want to check whether the next slide talks about that. No, it doesn't. Okay, so let me talk. I will draw a diagram because this is really necessary, but I need a whiteboard. So here's an example again from my recent job, but the same kind of thing applies to many things. So we would often be calculating, say, the total number of deaths across the world for a particular disease. We might be counting up everybody who's died from tuberculosis. And so we would, this would, if we ran it like one country at a time, it would take 3 weeks to run. And so instead we would use concurrency. We'd run one process per country. So that's roughly 150 processes for each country. And then after we'd done every country, we would then want to add up the country results for the whole world. Now, obviously, we have to wait until every single country is done before we calculate the world. Otherwise, the world will have the wrong numbers because it'll start calculating the total before all the individual countries are complete. So that's why you want to do a join. I am going to lift this up because I have to show you why it's called the word, or why it is used the word join. So there's two words that'll be used all the time. One is fork and the other is join. And so very, very classic pattern in all sorts of concurrency programming is where you do a fork into multiple jobs. The reason it's called fork is because it looks like a fork or a pitchfork, and then joins them all back again. That's where the word comes from. Right, so let's look. So here, let me just zoom in a bit again. Come on, you can zoom. So what we're doing in this, anybody have a, what do you think about this formatting here? No. Why do you think this has happened? This is a basic Java question. He's probably used tabs, not spaces. And so the editor's engine. So what I'm going to do here is just showing you some things, reformat the file, reformat the whole thing, so I don't have to edit it myself. Okay, can't scroll there, I have to scroll here. So again, we'll create an array of runnables. That just, of course, because this is Java, it just creates the array. Yes. Yes. Well, each thread is executing one country, yes.
Outside the multi-threaded part, so it can be accessed by one thread at a time.
Yeah, that's a very good question. The question, I think what you're asking is, would you use processes or threads? Is it? Yeah, well, we used processes at IHME because, see, if we, can I come back to that at the break? Because it's going to take 10 minutes, but you wouldn't do that country example using threads for reasons which I'll explain later. So here we have a naming runnable. Now, of course, that just creates the array. So here we actually create the runnables and allocate them in. We give them names. Wonderful. And now we're creating a thread for each runnable. As always, this is probably the hardest thing to grasp in Java concurrency is you create a runnable and thread, and then we start them all off. And then here, we're actually we do the join. So if we run this one, and if the code still works, it's always dangerous doing a live demo. Now I'm going to add something here. Where was it? Let's run that. Now you can, I'll come over this side. So you can see boring, constructors are called, great, the run's called. And now here you can see in these thread 1s through 4, you can see each thread running because all this thread does is writes out its name. But here, these waiting messages I put into this main loop while the main thread is waiting for its children threads to finish. And so you can see the main thread executing there. And it's doing what's called a spin lock, which is a bad idea because it wastes time. It's just sitting there occupying memory, waiting, which is to the question from the back, is why we would use processes, not threads. Okay, how are we going for time? It'd be easy for me to spend too much time coding. All right. Key points. I will go back into big mode. You create threads by the code is the runnable, that's the code that executes. The thread, the Java virtual machine actually gives you a core and a stack and all that, and it will actually execute it. They are different things. A thread has a runnable. Right. You start a thread with the start method, that returns immediately. The other thread is now running. The calling thread continues on and the other thread is now running. If you want to wait for it, you've got to use a join. The threads are independent, yep. The order of execution is non-deterministic. We'll have some examples of that in a minute. There are some examples in here that deliberately write bad code, and you can see what happens. I will talk more about the way statements overlap later. This should be threads of state machines. If you're curious about how threads, we're not going to go into that, but a thread, you create a thread, then you start it, then it's executing, they can pause, and then they're stopped. We're not going to go into details there, but that would be, for example, in this text. But it's pretty obvious. You start them and then they run and then they stop. Or they can die and throw exceptions. I recommend you look in the book for what happens when you throw exceptions. At this point, we'll start talking about what can go wrong. So here we have two threads. They each have a stack, as I was pointing out before. Method 1, method 2. They're running identical code, but they've got their own stack frames. They've got their own local variables with their own values. Now, local variable 1, perhaps that's an integer. It's small. It just sits on the stack. Local variable 2 is a full object, and so it points into the heap. Because you're all nice little Java programmers, the difference between a heap and stack. But unfortunately, variable 2 in both threads is pointing to the same object down here, which means that maybe thread 1 writes something into object 3, then thread 2 does, thread 1 comes back and is surprised by what it finds there. It's because they're both writing to the same, blackboard and things going wrong. So this is the fundamental problem with shared memory. The two particular ones that are hard is one's called a race condition. We'll have examples of that in a minute, and the other one is a deadlock. Now, race condition, this is from the idea of a race where you have two people racing to be the first one to get somewhere. The first one who gets there gets to place their order at the coffee counter first. The second one is later. You don't know which one's going to get there first. And so you will end up with non-deterministic results, meaning you can't predict what they are. And unfortunately, you'll probably only discover this in production. Deadlocks, if you've done a database course, you've probably seen deadlocks. The way to avoid race conditions is you use a lock. If there's a piece of shared information, then you put a lock on it so that only one person can have one thread, can have it at one time. But you'll get in a situation where you've got two threads that are both grabbing locks on things, and then they want a lock that the other guy's got, and it stops dead. More details on that later, but we just wanted to get it in there. Interleaving, yeah. So this, my laptop, for example, I think is a 4-core machine, but I can run 1,000 threads on here. And the operating system will allocate thread to each core and do what's called interleaving. Like if you take 2 books, this is where the word comes from, and you put the leaves like that, then you've got an ordering or a serialization. So the way in which all of those threads are run is up to the Java virtual machine and up to the operating system, and you can't predict what it is. All right, well, here's a tiny little quiz. So suppose we have several threads and they're all making changes to the same variable, which is shared in the heap. That's very important. And this is the way it works. First thing they'll do is they'll read the value from memory to the register next to the ALU. They'll change that in their own register, in their own ALU, and then they'll write it back to memory. Because the only way you can, I'm not sure if you've done computer hardware, the only way the ALU can work is if it's in a register. Then I'll write it back. Now suppose we have 2 threads and they're doing this. One of them's adding 6 to X and the other one's adding 1. What do you think the result would be? Seven, if you're lucky. If the 2 threads, if thread 1 runs and adds 6 to it, and then thread 2, then it's 7. But you can't guarantee that that's the order you'll get. This is the order. If you're lucky, you get 6 plus 1 is 7. If you're unlucky, and in fact you will be unlucky, you can see this. I'll come over this side. So the first thread reads X into its register. It adds 6 to it. It writes it back to memory. So main memory now has a value 6 for X. But in the meantime, so that's the good case, sorry. So this case, it reads X into its register. It adds 6 to it. Now thread 2 starts, it reads it, and so it's got let's just say X starts with 0. So this point X is 0, now X is 6 in its local memory. This guy reads from memory, so he's still seeing 0, because that thread 1 hasn't written back. It adds 1s to it, it writes 1 back to main memory. So at this point 1 is in main memory. Now this guy writes back, and he writes 6 back. And so main memory has 6. And you can imagine it could be around the other way, and you end up with 1 in main memory, not 6. And so that's a race condition, because depending on the relative speed of the 2 threads, you'll get one result or the other. Well, you can get any sort of result. And this is a fundamental problem this is the problem in concurrent programming. Yes, it could be 1, 6, or 7 in this case, 3 values. Yep. So this one, how are we going for time? Are we up to an hour yet? Not quite. Right, so I threw this slide in just because, again, I understand things better if I understand the hardware that it's working on. And also, we just talked about registers, and without saying this. So the register, there's a whole hierarchy of memory. Sorry, have you guys done computer architecture? A little bit, but probably. So is this familiar to with a memory hierarchy? Yes, no, not everybody. Good. As long as not everybody. So the registers are really fast. Access to that is 0.3 nanoseconds. That should be capital S. No, it shouldn't. So that's really fast. That's why the ALUs work. Then each ALU has a cache. Let me explain. A cache is a copy of memory. of the main memory. Then typically each pair of processors share it, and then typically the whole, like more pairs, and then the whole die, and then main memory. So when we're talking about reading from main memory, in that previous slide from thread 1, it's reading from main memory all the way up to the register so it can operate quickly. And it's an interesting slide there. Okay. I think we've already talked about this. This is the fundamental, the non-determinism. Okay, so let's switch back to code. So this is request counter bad. Whoops. Let's go back to the code. Thank you. By the way, which Java IDE are you guys familiar with? Visual Studio, okay. Yep. Okay, so this is a intentionally bad piece of code. And it's going to create 1,000 threads, and then it's going to let them all access the same variable. So sorry, I'm just reading for a second. So yeah, here we're doing a lambda to avoid creating the runnable. So what the runnable in each thread is going to do is it's going to increment this counter. And so all of them are going to be attempting to update this same integer up here. And so we should be seeing the situation, though, even though they each add 1 to the counter, and if it was deterministic, we'd see 1,000, because they might be reading at the wrong time, we should see something a little bit less than 1,000. Let's run that. Is it 1,000 or 10,000? It's just 1,000. Okay, this is a problem. It works. Okay. See, it says the value should be equal to 1,000. It was 1,000. There was no actual race condition. And as the sysad, so it magically fixed itself. And as a very good system administrator I knew says he hates things that magically fix themselves because it means they'll magically break later. So I actually had to change that. So what I did here is I added what's called jitter. And jitter means a little. It's like if you drink too much coffee and you jitter. So I've added each one of these threads. Let's come down here. Will sleep for a very small amount of time before it tries to update the shared variable, and the amount of time it sleeps for is random. I've imported the random package, and so they're all going to sleep for a random amount of time, which will mean that some of them will go fast, some of them will go slow, and this will force a race condition because they're not all going to be nicely well behaved. All right, and so I ran fewer threads, and you can see there the result was 485 rather than 500, which means there was 15 cases where it read a stale value, or read an old value and then wrote back. The thing you get from, there's two lessons from this example. One is that race conditions, they're hard. They will show when you're up when you don't want them, and they won't show up when you do want them. And the second thing is it's caused by slight changes in execution speed. I actually found this quite funny that it worked properly. It's also interesting that my machine does not have 1,000 cores. So the Java virtual machine has executed the threads in a safe order, which is surprising.
1,000 virtual thread, and it is being uh, individually processed through each of the cores in the system. So how that 1,000?
So the question is, how can we actually run 1,000 threads on a 4-core machine? Well, this thing just orders more cores and they arrive by Amazon. No, you're quite right. It's either the Java virtual machine or the operating system. I'm not sure which will it has a pool of threads. It has 1,000 thread objects in Java, and probably every 100 milliseconds it will stop the current thread, pick up one from the set of threads that need to run, and actually give it a core. So the operating itself is multitasking. Well, sorry, is spreading the physical cores across the pool of virtual threads that need to run. Yeah, no, it's a good question. That's how you can run more of them. This thing has 4, more modern ones have 16. Big machines that I'm used to would have 80 or 128 cores. It's interesting that whoever created these slides, their machine behaved differently, and they were getting it was failing for them. I think we'll stop here, take a 10-minute break because it's a change of subject. We're about to talk about how you can avoid race conditions, and we're about so come back at 11:10. And if you've got any questions that you want to ask now, if you've got questions that you were too embarrassed to ask during the lecture, you can ask now.
还有一个 data mining， 本来想选就是周五，就是那个另一个讲师，然后那个课嘛，我昨天排上了 waitlist， 但是排上了。
Yeah, that repo.
Favorite set of classes. Yeah, it's like every class. I'm studying the next Thursday. That's the biggest. It's the key to they try to. Oh, okay. It's not my ass. It's all in their head. I got much of it. I haven't looked at this on yet. I got saved there. Rival. What was the first one? Yeah.
但是加一个 note 就是老师现在讲是最多4个，最少4个4个，那那个database 最少data 3个啊 database 不是 database， 我上的是 data mining， 就是machine learning 那个你说的是那个520
加的那个。
520哦 database 是多少个来着？6我的下学期上那个下学期还要上一个，我还以为你没有我然后就还在等 return 结果，昨天就我们的公司 VP 基本上下部的基本都开完啊 VP 才那个疫苗的好 VP 才那实习5个月。然后我就挂一个面，他考的就是考现招吗？我之前以为他不指招或者是有身份限制，现招就是还没来那个女生，她就进了 OCA 啊，11月份。他让我写一个 reader writer， 这估计马上就讲了。今天中午那节课人超多，没座位。他讲的好，感觉他口齿可以能听清楚。是因为是向外上课？没有，我只不过就是他们跟我就是很多人推荐那个教授，那个教授是因为只有那个老师，对，只有他这个很新来。我之前是我看那个包满了嘛，我也类似满了，我就第一人发言讲，我说你网课来教一下，他说他好。而且就是不一样的性质。
That's mandatory. Yeah. It's easy. I try to. Yeah, Emacs must be easy. I was trying to figure out for like the longest time how to like format the pseudocode and everything because it would not work. But that's like a whole new language. But it's like simultational. It's not bad. It's not too bad. What's your name? John. You're a senior. Oh, you started at spring.
那类似能把我加进去，说可以啊可以啊，然后再把我加成 observer， 把我加成旁听，真的行，逗。还查我说怎么还在 waitlist？ 本来已经把我加进去了，还给我专门发邮件，看是 observer。找一点 IC， 有可能啊，因为我 project 做的挺好的，老板说，如果是他选，他会下。
It's like the onion. It wasn't so much, so they were noticing. And then after that, he was like, man, I'm not in a city.
You're not.
So
You didn't like the city. It's like it's a bit of a
island and a touristic place, so it's not like a city like some. So
Oh, it's not in downtown Boston.
no. 5 hours away now.
Oh, interesting. Not too much to do. Less to do than Seattle. You were less to do than Seattle.
Yeah.
What would you do? Is that considered like MLE or? Are you gonna do like more AI classes? No,
I want to do a lot of software.
Okay. That's why they distributed the software. Okay. I feel like this might be more useful than
Yeah.
the AI. Because I've heard they teach a lot of just pure theory.
Yeah, that's why.
Oh, the AI class.
Yeah, that's why I think we should do projects. Would be better if we want
Just do the projects.
projects. That could experiment.
Did you do research? I feel like research is almost mandatory for.
这样，因为我今天是要半节课没有选这个课，所以我不能。最后的那个二战，对。之前啊，这样子，我还以为就是上课过程中就会这样一点一点做完。
Usually work with. Yes. It's kind of interesting. I think we have to do some part of the code in like C. So that's that's the only thing. Like, I wish I knew C. Yeah. Still wish I knew C. I have like that one coding book that everybody has, like the primer, like. I got. And one class I really wanted to take was the computer vision class. Oh, I feel like that one sounds good. And that one's also really good, yeah. But it's fresh, nice. English. English. You remember which was it? Or the no. I didn't take it, but it's all hearing. This one, okay.
Region, US West or US East? I think I'm supposed to use US East. The written instruction said US West, but I found that it wasn't. And so I used these things have changed since last year. And then I'm trying to remember what the visual guide said. I was hoping to go through afterwards, after the lecture.
All right, back from break. I had a question about threads versus runnable. This is the fundamental part, so I'm just going to go over that again. And I'm changing some names here to make it exactly clear what's going on. So there are two things that you need. You need a runnable and you need a thread. And let's go to the runnable. So the runnable has one job, which is to implement the run method. That whatever it is you're going to do, maybe you're going to handle the web request coming in and go and buy shoes for the person who's shopping on Amazon. Or maybe this is a scientific computation, and that's where you're going to calculate the number of tuberculosis deaths in that country. Now, a runnable is a class, so we do create objects of it, but it implements the runnable interface. Runnable is just an interface, and it just defines one method. So coming over here, I'm using the refactor to make it clearer, because these are not names, they're not strings, they're runnables. And again, I emphasize that names are important. And so this makes it a bit clearer that the threads are constructed with a runnable, because the thread just gives you access to the core, or as was pointed out, it will eventually give you access to the core. The runnable is the actual code that's doing something. And so here we create, each thread has a runnable, and then you start the thread and that executes the run method in the runnable. So I've just added a few comments in here and changed a few names that I hope should make it clearer. And I will commit this code after the updated slides after this lecture. So I just want to emphasize there's two things: threads and runnables. You will work that out immediately, because the first half of lab 2 is all about this programming. So you won't be able to avoid it. Okay. So how do you get around race conditions? You do what's called synchronization. And in fact, in Java, that's the exact keyword. It is synchronize. And you also, whoops, I wanted to emphasize that. The word lock is the word that's most commonly used. The idea that you lock something so that nobody else has access to it. So one thread locks it and they have access. There's another word that is used, which is serialize. I'll draw that on the board in a second, because the JVM or the operating system will, if it's got many threads or many processes, it has to, if it's, say you've only got one CPU, it's easy to understand with one core, it has to run one thread after another. And so that's called serialization, meaning laying things out in the serial order. And so the operating system or the virtual machine is responsible for serializing the order of the execution of threads. How do we use locks? So if you've got a variable that's protected by a lock, the first thing the thread has to do, it has to get the lock, then it changes the variable and then releases the lock. In fact, there are even some hardware instructions that do that for you. So it's physically impossible for anybody else to get in the way. While the lock is set, if other threads want to access that shared variable, they have to wait until the lock is released. And that, of course, is what can lead to deadlocks. So we will cover that with Java synchronized and monitors. Locks are sometimes known as semaphores. This is a semaphore. It's a railway signal. And I think the reason that this word was used is locks were invented by a computer science called Dijkstra. He was Dutch and he used Dutch words for things. And so the original meaning was semaphore. But you won't see semaphore. Mostly you'll see the word lock. But that's the concept. You only want one train on a track at one time. So. Right, so here is an example of it in Java. There's the synchronized keyword. This is where locks come in. So what have we got on this one? Only one thread can execute the increment method at a time, and only one thread can execute the decrement method at a time. This is known as a critical section, the word critical because it's shared. It's not possible for two invocations of any synchronized methods on the same object to overlap. Now I notice that, yeah, Vishal used the word interleave there. I think the word overlap is correct, but I need to check with him as to what shows up on the quizzes. See where it goes. I just want to check on it. Yes, that's the next slide. You can have the words, we'll see synchronized later, but synchronized can either be on a method or it can be on a section of code. The key thing is that it applies to an actual object. So the lock is associated with one particular object. So each instance of synchronized counter has what's called a monitor in Java, which is a lock, and only one thread can execute any one of the synchronized methods on that object at a time. Yeah. This is, you probably want to read a longer explanation in this one because it takes a little bit to understand what's going on here. So, but there is code example in a minute, which will probably make it clearer. So the key point is that if you put a synchronized on a method, and typically you want to do it on a method, then only one variable can get in there. Sorry, one thread can access at a time. That was the original method the original mechanism in Java for doing it. There are newer systems for doing locks that are less heavyweight, and there's this whole sequence of sort of extended basic types that have locks and are just a little bit easier to use. So you can create an atomic integer, atomic meaning that it's indivisible, and this also has a lock on it. So if anybody goes to try and update it, then there's an automatic lock on it and only one thread can execute at a time. They're described in the book or in the Oracle, in the Oracle documentation. I'm just looking for where we get to the, yeah. Okay. So the key point I want to emphasize is you put a lock on the object, and then all of the synchronized methods for the methods on that object are now protected and only one thread can go through them at a time. Yep. The monitor is part of the JVM. So it's associated with an object, but only the Java virtual machine has access to it. And so when the first thread enters a synchronized method, then the JVM updates the state in the monitor. When that thread exits, the JVM changes the state in the monitor and then calls notify on all of the waiting threads. And one of them wakes up and is lucky to get the control of the monitor and moves on. I know that's in the text, but this lecture is a little bit of a quick pass through concurrency. By doing the lab, you'll learn it all. So there's a notify method as well. Okay. This one, the barrier synchronization, is very similar to the join example we used before, where you want to make sure that you've got a number of things happening and then they all leave at the same time. You know, like loading a train. You've got to wait till everybody's on board the train before it leaves. The way there's a primitive for doing this in the more recent concurrency package called the countdown latch that implements a barrier. It's just a different way of doing, instead of using a join, you can use this. And the key method is await. There's an example in a couple of slides, so don't worry about it. The await will block until the counter, the latch, has reached 0, and then you can move on, and a countdown decrements it. You'll see this in the example. But I will rather walk through it in the code. So there's a latch. Right. So that's request counter barrier. So let me switch to the IDE. Thank you. And I'll just double check that that's the right code. Right. Okay, so here we have, this is the shared resource, this counter named count, because it's on the object. And what this will do, this main method, is we're going to use a lambda to create the runnable, so that we don't actually have a separate class for the runnable, but it is creating an object that implements the runnable method. Hopefully you've seen this lambda style in your Java course. And all it's going to do is decrement the counter, and then it's going to say, I'm done. And then we're going to start the thread. And again, we're going to see whether it works correctly. Yep, and it does, because this JVM is well behaved. I didn't put jitter in it here. In fact, this one is going to be well behaved because you've got synchronization. You've got this countdown latch. All right. The main thing to remember from the last sequence would just be the use of synchronization, the use of monitors. I wouldn't worry about the latch. If you ever need to use a latch in industry, you'll go into Stack Overflow or use ChatGPT to generate the code and then work it out. The thing to remember is synchronized and monitors. Now we're going to change gears and we're going to talk about deadlocks. And the classic example was one that was invented by Dijkstra, called the dining philosopher's problem. It sounds very theoretical, but I can tell you that this is a really very good way of explaining the problem, and it shows up all the time. And I know inside places like Azure, in their file system, they have things called Paxos rings to solve this problem. So the way this is always described is you've got a set of philosophers who are sitting around a table, and they alternate between eating and thinking. And in the classic example, they use forks, but that doesn't work so well because you only need one fork to eat. It works much better with chopsticks because you need two. Because the fundamental problem is that these two philosophers are going to argue over who gets the chopsticks. All right, so some pseudocode for it. So okay, it's written in forks. I was saying short, but they've got to pick up the left one, pick up the right one, and then they can eat. And then and once they've finished eating, they put them down. But the problem is that you'll get deadlocks because one philosopher picks up one chopstick, goes to pick up the other one, and the other philosopher's got it, and you can get a situation where they're all waiting for the other philosopher to let it go. And that's what a deadlock is. So here we have an example of, we can just see it. So a philosopher is going to be a runnable, and you can see there it's implemented the run method. So this is what a philosopher does. They do some thinking, and they're going to sync. So this actually shows the solution to the problem. The solution to the problem is don't let them don't let them pick up any random chopstick. Instead, we're going to have a particular order in which we're going to pick up chopsticks. We're always going to get the left one first. If this was a database course, I'd spend a lot of time talking about deadlocks and about why you want to have a defined sequence. But just believe me, if you have a defined sequence of getting locks, it means you can't get into problems. So the way this code is written is you always get the left fork first, and then you get the right one, and then you go. Because the first, let's come back to the diagram. So I've got it to point out. Right, there we go. We'll come over here. So if Socrates here grabs this fork first, chopstick, and Plato has grabbed that one, and now Plato attempts to grab this one, Plato will wait on that chopstick because Socrates has it first. Okay, and then Socrates can grab this one and can eat and let go. Now Confucius, who's sitting here, attempts to grab this chopstick but must wait because Socrates is currently eating. As soon as Socrates is finished, Socrates releases the right fork. The JVM notices that they've exited the synchronized block, releases the chopstick. Confucius has sent a notify method, can pick up this chopstick, and then we'll go grab that one. When this needs a slide. I really need to put a slide for this one. When Socrates puts it down, that chopstick goes down, Aristotle can pick it up. And so that way we avoid getting a deadlock because there's a defined order and using the synchronized method. This particularly comes up in databases where you're locking tables. There it is serialized. Here's an example of a deadlock. So thread one, if they take A and then but the other thread takes B, thread one tries to get B, can't because thread two's got it, and then thread two tries to get A, and they're stuck. Draw a diagram for that, because this is. Has anybody have you done database courses where we've talked about deadlocks, or is this a new concept? Who hasn't seen a deadlock before? Or who's asleep? All right, not going to draw a diagram. I'll put one in the slides for next time. Okay. Yeah, and so in the lab you'll be doing this where you're putting what's called a total ordering on the acquisition of resources, and there you see it as a second bullet point. If you do the total ordering, then you can be guaranteed that you cannot get a deadlock, because if somebody's up to here, they won't. Well, don't have time in the lecture to explain why, but total ordering will prevent it from occurring. So you always have to get chopstick 0 before chopstick 1, and that breaks the circle because you have a defined total order. Total order means that it's a word from algebra in pure mathematics. It means that for any two objects in a collection, you can know whether one's greater than the other one or not, compared to a partial order. And then we've got the solution. Yep. That's in pseudocode. Yeah, some warnings about synchronization. It's difficult to get right. And this is a case where you want to use what's called minimum viable product. First, you make the code work, and then you make it fast. So you start by putting synchronized keyword on whole methods. It's possible that the critical section logically is smaller and you can just put it on a block within it. But the problem is the smaller you make it, yes, the code will run faster because the locks are smaller, but you're likely to make a mistake and you're likely to reintroduce the race condition. So you're better off making it safe and not lock up in production. Testing, yes. So your unit test probably won't pick it up. Unit test will test the logic, the business logic, the application logic within that class and all the classes that it calls. But because it's non-deterministic, you can't guarantee that you'll get a bad ordering that would create the deadlock. The way that people try to solve this is you'll run some kind of scale test for several days. Right? For example, the job control system we did at the university, we would bring up a test server and then we'd run 1 million random jobs for several days in all sorts of different orders, just with varying speeds and varying counters, trying to find a deadlock condition or a race condition. Yeah. Yeah, if you have to have a total order over all the things you're going to lock. Probably easiest to talk about this in a database context. A database schema will usually have several hundred tables. Now, in a course, you only ever see database schemas with like 5 tables, but in practice, they have hundreds. To define a total order, you'd have to have a total order, meaning an order in which you're going to acquire locks across all the tables. And you'd have to communicate that order to all the other teams that are doing it and who are using it. And that's where it'll probably go wrong, because you'll probably fail to communicate to one other team. This bullet point is a bit too short. Rather, it should say, if your ordering constraints are too complicated and too large, then you'll make a mistake and you'll get to deadlocks. That's really what it's trying to say. But I emphasize thorough testing is impossible. The big cloud companies, I know, the way that SAT works at Amazon is you run, their unit tests will run automatically. I assume that you've learned about DevOps and automatic testing. No? Yes? No. Okay. So the way it works it works in a proper production company is when you commit your code to Git, it'll create a pull request, and everybody else in your team looks at it and comments. And when that's all happy, and actually as part of that pull request, it will run all the unit tests. And a unit test just tests the logic in that one class and all of the other classes that it calls. But it's only probably running in one thread. So it's not going to find any of the race condition problems. So then once it's committed, then your build system will automatically deploy it to a small cluster with, say, 10 machines, and then maybe 100. And so what it's trying to do there automatically is find places where you've either got load problems or race conditions or deadlocks. And that's done automatically because it's hard. Okay, I actually lied a little bit. We do have a slide in here on this is the state diagram for Java threads. So when a thread is constructed, it's via the new method, which is calls a constructor. It's in the started. It has a runnable. It started. When you start it, then it becomes, that's probably a poor word because this isn't the runnable class. What it means, it's available to be run. It's in a state where it could run. Now, if there is a thread available, it will actually run. If it now encounters a lock, tries to go through a synchronized section, it can't. It goes in. It's put onto a different queue called blocked. And then it can be resumed and runnable. Eventually, it'll finish and terminate. Yeah. So if it's in the running state, it's either currently runnable or it's blocked because it's waiting for a lock from somebody else. Now, I haven't mentioned it, but of course, if your code has a problem and throws an exception, it'll instantly go down there. If you don't catch the exception, the thread dies. So what would cause your thread to temporarily halt, meaning to not be runnable? If you call sleep, you might deliberately do that. The example I had in the jitter one, I put the individual threads to sleep for a little while so they would move off the runnable queue and onto the waiting queue. You can also call the suspend method. You might know that for some reason in your code that you want to just wait for a while. And then there's the wait method, which waits until there's a notification of a free resource. This is all to do with the monitors on a synchronized section. And the last one is out of your control. If you call an IO, if you go to try to read a file, then the VM and the operating system will take you off the runnable queue and move you onto the wait queue because it's got to wait because it'll take a while before the data comes back. And then, so how do you come off that queue? So if you were asleep and the timer goes off, then you call interrupt, it comes off. If you're suspended, somebody else can resume you. Again, the details of that are in here, or you could go look at an Oracle tutorial. But if a thread can suspend itself and then somebody else can wake it up using the resume method. And the third one is the most interesting. If you're waiting on a condition variable, then the person who the thread who lets it go can call notify, which will wake up everybody who is waiting on it. Just want to look for the example of that. Yep, it's not there. I think it's a little bit later than I was expecting. And of course, if your IO completes, then the operating system talks to the JVM, and the JVM moves you from blocked waiting to runnable. This one is a little bit advanced. I wouldn't worry too much about it. You can give in your code, you can set the relative priority of threads so that some threads will run more frequently and effectively run faster because they get a greater share of the cores. So there are priorities you can set on a thread when you create it, and the higher the integer number, the more share of the cores it will get, and the faster it'll appear to run. Most of the time you don't worry about that. Most of the time you're running of it all the same. But it is there. Okay, so what we're talking about here is that the Java virtual machine, the JVM, is in charge of choosing which thread to run next. So when a core becomes free because maybe it's the existing runnable on there is gone to sleep, or it's doing IO, the JVM has to choose which thread is going to go onto that core next. And there are various algorithms it could use, but the one it does use is a round robin one. So it chooses it looks at the runnable queue, it chooses the thread that's on the waiting thread that's got the highest priority and puts it on there. And that chosen thread will then continue to run until for example, it exits or it yields. It could pause itself, or or its time allotment has expired. The way actual kernels operating systems work is there's a timer that goes off every so often called a time slice. Maybe it's 100 milliseconds. When that goes off, the operating system wakes up, it gets control of the CPU, and then it will look at the runnable list and see which thread's running and make a decision whether it's in the interest of fairness, whether it should pull one of the running threads off and put another one in. And that's called liveness. It's discussed in the texts, because you don't want to leave one thread running on a core forever, because then the other threads that are waiting never get a share. And so this time slicing is what actually shares threads and processes across the CPU. Okay. Sorry, I'm just going to have a drink. Right. As I mentioned earlier, and now we're going into details, the Java object has a lock associated with it. Every object has a lock. It's called a monitor, or sometimes a mutex, which is short for mutual exclusion, meaning only one thing can be in there, everything else is excluded. But they usually call the monitor or a lock. All synchronized methods interact with that lock. And when your code enters a synchronized block, which can either be a method down here, or you can put it on a block, which I don't recommend, then the JVM will grab that lock for you on that object. You do your stuff, and then when that thread exits the method, then the lock is released. And this is done automatically for you by the JVM. Now, if you're working in C++, you would have to remember to to grab the lock and release the lock yourself, which of course means from time to time you'll forget to release it, and you've now got a bug because you grabbed an object and you're holding it on forever, and now you're probably going to deadlock the whole system, which is why we're not working in C++, because it's just more likely that you're going to make a mistake. So, right. Now, what this bottom piece of code is explaining is that there's a base class here called the hipster base class. I think this is dating a bit. I don't think we use that slang anymore. And then the cap hill bar extends the hipster base class. They've both got synchronized methods, but if you create an object of capital hill bar, it's got one monitor, and it uses the same monitor for both the order drinks method and the do hipster stuff method. So if a thread creates an object of this class, calls this on it, then the superclass method is also what is it called, blocked by that semaphore. Yeah. Okay. So. I will talk about this slide, but then go back to the other one to actually show you the code. Actually, I'm going to write this on the board. I'm going to write it here. And I'm going to use short names. So if we have two classes, base and derived, and this got F, and I'm not going to write out the full syntax. F is synchronized and G is synchronized. And we have a thread over here, which is, of course, had some kind of runnable. And in the run method for that runnable, what it does is it's created an object of class derived, and they should be capitals because this is Java, so they're supposed to be capitals. I probably should do this in an IDE. Then if you call G is is a synchronized method in the derived class that will actually grab the monitor for that whole D object, and so this thread can safely call F as well, even though F is on the superclass. This is, of course, is one object of the D, and it can work, and it can do that. If it had a different one, well. No, I think I'll stop the example of that. So what this slide is trying to emphasize is that where is it? Yeah, if a thread tries to acquire a lock that it already holds because it's already called a synchronized method on that object, then it succeeds. You don't lock yourself out. I'll lower that in a second. I'm going to pause. I mean, you'll have to do the lab to really get this because it's a classic case of, hear and you forget, see and you remember, but do and you understand. You're going to have to do this to really get it. So I'm sure that you haven't quite understood everything, but I'm going to emphasize you really need to do the labs. The reason we're doing concurrent programming in Java because it's a safe environment in which to learn concurrency. We won't be writing threads in Tomcat in the longer examples, in the longer labs and assignments, but if you don't understand concurrency, you'll get in trouble there. So do the Java so you understand it. It was where I was at the university, it was a fundamental thing. You really had to understand it. Those who didn't created bugs and then spent all weekend dealing with it. Okay. Here's a classic example. And actually, this is the guts of a web server that hides all the threads from you. It does this. So this is this is not theoretical. So what we're going to do is we're going to have a set of producers, threads that produce things. You could think of this as these are probably requests coming in from the internet. and then you've got a single data buffer, and then separate consumers. I'll come back to the web server example in a minute. So the consumers, these are the things that actually do the work, sometimes called worker threads. They're going to, if there's nothing in the data buffer, they will just wait. There's nothing to do, so they're just going to wait there. As soon as something appears here, one of these consumer threads will grab it and then go off and consume it, do the work. If this was a web request, this is probably some Ethernet controller, the first, and it comes in the Tomcat, because you're using the Tomcat web server, will wake up one worker thread and it'll do it. Now, on let's be even-handed, produce a bit of liveness. The producers can't fill the data buffer up if it's full. If the data buffer is full, they will wait. As soon as there is space here, it will be able to write. Yeah. There's a word here that's used, guards, which is just the concept that there are guards here to make sure it doesn't go over. It's just a different way of looking at it. Just as an aside here is there's no point having a data buffer and like this if they're working at different speeds. You do this if you're getting about, say, 1,000 TPS here, 1,000 transactions per second, and you've got the ability to handle 1,000, but the rate goes up and down, and so you need a buffer that will smooth out that rate. If the rate of arriving requests is fundamentally faster than your consumers, then this thing's just going to fill up and they all block. On the other hand, if you've got more consumers than you need, this buffer will always be empty, and so they will block. I hope to talk about Kubernetes later, and I'll talk about auto scaling, which is how you avoid that. Okay, now we're getting into the details of Java monitors, the wait and notify statement, which I mentioned in passing, but this is how it actually works. So wait is the method that the consumers will call if the buffer's empty, and notify is the method that the producer will call when they put something into the buffer and they want to notify some consumer that they should wake up and consume whatever is in there. Let's look at an example. Now, I've only got this on the slide. Actually, let me just double check. I think that's down in the other directory. Faster. Yep, it is. Okay. So here we're going to set up the main structure. So we've got two, in this example, we've got two consumers and we've got two producers, and they're sharing a buffer named drop. And so in both cases, the consumer and the producer take that as an incoming argument. Here is a consumer, takes in a buffer as a constructor, hangs on to that. And here's the run method, which it must implement because it's extending runnable. And so what it does is it attempts to retrieve something. This is a consumer, so it attempts to retrieve something from the buffer. This I'll talk about done in a minute, and then it just prints it out because this is a hello world example. What this is doing is this is a way of shutting down the system by sending a message in that's called done. Let's look at a producer. So this is a this is an example of a mock. I'm not sure if have you come across the concept of a mock in testing? Maybe. So this is pretending to be a system that's sending messages in, but instead, rather than being a real system sending messages in, it's got this little array, hardwired array of some sentences, and it's going to send them in. And so what it does is it goes through that array, puts them into the buffer. Okay. Let's come back to the slides. Right. And then we want to talk about the retrieve and the buff and the put method back here. And we go back to our main, pick that up. Sorry, I'm just, no, I don't. Okay, so put is the one that's called by the producer. And so what it does is, okay, wait until the message has been retrieved. So this buffer only has one cell in it because it's got one message. So this is a very small buffer. Unlike the diagram that was drawn where it had like 6 or 7 cells where it could hold things, this one only has one. And it's named a message. Empty is a Boolean that will keep track of whether there's something in there. So as long as it's empty, this is retrieved. So let's look at I want to look at the producer side. So the producer cannot write to the buffer if the buffer's full. The buffer is either empty or full. Not empty, of course, means it's full, and so the producer will wait. And then eventually it will be notified, and will therefore this will be true. It will be sorry. It'll actually be empty. It comes out, sets the fact that it is now empty. It's no longer empty, and it puts something in there. This is all synchronized, which is very, very important. Once it's pushed its message in there, it will call notify all. Notify all is a built-in messaging method in Java, and it's telling the JVM to notify all the other threads that are waiting on this object. So waiting on the object of instance buffer. So some thread has come in here through put and has therefore acquired the lock on that object, the monitor on that object. It's doing its work, and then when it's done, it notifies all, exits, the lock is released, and this notify all will cause the JVM to wake up to send notify to all the other threads that were waiting, and one of them is going to continue. I won't go through retrieve. It works pretty much the same. Well, maybe I will, but just not at the moment. Because let's go back to, say, consumer. So, yeah, actually. So here's a consumer, and it's going to call retrieve. But in the beginning, the buffer is going to be empty. So I'm going to draw over here. Be nice if I had a way of turning this off, but turning off one projector at a time. Okay, so we start out with the buffer being empty. And the consumer wakes up. Is this the consumer up here? I hope it is. That's the buffer. So the consumer is going to call retrieve. And retrieve is a method on the buffer. And so I'll actually write it come down here. So the consumer, and it's going to be consumer number 1, calls retrieve, that gets the lock on the monitor. So I'm going to draw a little monitor down here. It currently, this is consumer 1's thread has the lock, but because this is empty, it's going to wait because it can't consume, there's no thing. So wait says, I can't proceed. It releases the lock, but the JVM puts it on the, there's a little list inside the JVM of threads that are waiting on it. And so this consumer is actually put in that queue. Now, the producer thread wakes up and it does a put. Now, the P1 thread might have been waiting while C1 was starting, but now that C1 has called wait, it no longer has the lock on the buffer because it's waiting. It's down here. And so producer calls put, it acquires the lock, puts a value in there, whatever it is, something about mares eating oats, I think. Yeah, oats in there. And then it calls in the put, sorry, this one. It calls notify all and then it exits. It exits the synchronized region, so it no longer holds the lock, and notify all will cause the JVM to wake up every thread that is on the waiting queue. And there's only one of them. And C1 now picks up from where it left off, which was in retrieve. So it's woken up, it checks, is it empty? No, it's not anymore. So that while loop exits. It marks the fact that it's empty, excuse me, notifies all, and it returns a message. I suggest you run this code with a bunch of printouts, so print statements, so you can see how it works. But this is the fundamental. This is a really good example. We've got a single object, just to emphasize it, single object in the middle. It's got this monitor here. I'm sorry that I'm facing the board, but all right. And only one of these threads at a time has the monitor. And then when they call wait, they yield the monitor, as it's called, and move down into here. In fact, in Python, it's called yield. Notify all. If there were multiple consumers over here, suppose we had consumers 0 through 2, and they might all be waiting on here. And notify all will notify them all, but only one of them will be the first to get the lock and will proceed, and the others will actually block again. And that can lead to, that essentially is a race condition, but at least the JVM keeps it safe because only one gets a lock, but it can lead to a problem known as liveness, meaning that some poor thread gets starved, never gets the core, never gets the object, and isn't live and dies because it's hard. It's a hard thing in system design to balance safety with liveness. I know that in this book, Doug Lee talks a lot about the different problems there. We don't have time in this lecture, nor is this an entire course on concurrency. But oops, I think I just moved a thread. Slide Java guards, wait and notify. Yep. Yes.
So you by the time they call the wait method.
Yes, when the thread calls wait, wait is a method that goes into the JVM, and the JVM takes them out of the monitor and puts them onto the waiting list. No, this is, I should use a different colored. This stuff, everything in black is under control of the JVM and your code cannot access it. I mean, actually, I would have to check. It might be possible to find out who's waiting, but you certainly can't fiddle with it. Because you could imagine a badly behaved thread might change disorder so that nobody else gets a chance to run. Yes. Yeah, that wouldn't be nice. All right, so here's some interesting questions. What if you had an object that has no state? Right. Now we've used an example with a buffer that's got state, it's got a cell. We've got an example where we had a counter that's got state. What happens if an object has no state, it has no local variables? Do we have to synchronize? Do we have to protect it? Thoughts? Yeah, I'm hearing no. No, because there's no way that you can cause the other thread to be confused because there's no shared state. There's no possible cause of confusion. Stateless programming is very important. When we actually get to talk about RESTful servers in Tomcat, it's best if your threads are stateless for this reason. Your services are stateless. Yeah. There we are. Next slide. Let me bump this down. You will deal with servlets in Lab 2 with Tomcat. A servlet is the worker thread inside the web server. When a request comes in, Tomcat will start up your servlet, and this is where you write your code. So servlet is a base interface. And then there's an adapter class called generic servlet, which provides a bunch of useful stuff. So in this case, the final class stateless factorizer is extending that. Actually, before we go to servlets, how far are we into 50? Let's just take 5 minutes. Yep. And then we'll do 5 minutes because I want to be able to fit in some time at the end. Do you need a break? Yeah, okay, 5-minute break. So 12:08, we'll come back.
So previously you talking about the loss in the database, are you talking about the reader writer? Like
Yeah,
what?
yes, like producer, sorry.
It's not just small is less. That is for that. You can do the same. Else you won't buy any good books. So you can go to the University of Washington Library. It's free for public. I think there are some books there. But actually, well, if you happen to go often, like you can almost like explore that library. I have been in here for them. To be honest, that one was kind of give me or any idea.
Just, yeah.
So with the other class, oh, you're using momentum too. So this doing your tabs. I have taken like database management system. What did you MS? Messages we have. What did you take? Database. I took the database management this semester. Yeah. So I'm taking machine class. I'm going to your class on Thursday. Check it out. Oh yeah. I heard it's okay. So which course did you end up? You have to pick like. Yeah. Yeah, that's what they say. Because this class one. Well, you have already chosen this course. Did you get like AWS account like? What is the name of these? I'm good here.
Looks like 5 minutes, not enough. We're still missing a few people. Okay. So this is an example of a stateless servlet, which is an example of a stateless thread. If you remember a few slides ago, I was asking about, is it safe to share access to a stateless servlet? A little bit of a story here. The word servlet was invented by a friend of mine when I was living in Sydney. He implemented a web server called Jetty. This is before Tomcat, before there were Java web servers. All of the dynamic web pages used to use Perl, and you'd have a Perl script sitting in the CGI bin directory, and the word servlet was coined because it's similar to the concept of an applet, which I don't think is really used anymore, which was an Java application that sat in a browser. And the concept of a servlet is a small piece of code that you as the programmer write that sits inside the context of the web server. So in Tomcat, what you do is you're always writing servlets, but you'll never write your own base one from servlet. You always use an adapter. So I'm not sure, because I don't know what you've learned in Java. An adapter class is one that overrides and implements all the annoying methods that you couldn't be bothered implementing yourself, and then you go and implement the one that matters. So the one in this case that matters is the method called service. The servlet request method it contains all the information that the person sitting at the other end of the browser, all they've typed in, it's sitting in there, all the parameters. And the job of a servlet is to read the stuff out of there and to write it back. Now, this particular example, and I'll swap sides, what it does is it gets a big integer out of the request from the user, It then factors it into its prime factors, and then it sends the prime factors back. So this would be a website with exactly one field in it. You type in an integer and you ask for its prime factors. So when you press the submit button, your browser sends an HTTP request to the web server. Tomcat gets that request, puts it into this object, calls your servlet.service. Your servlet uses the request object to get the integer out of there, and it could be a big one, so it's using big integer, not just straight integer. It can be an arbitrary length integer. Calls the prime factorization function and writes it back into the response, and then Tomcat has the responsibility of returning it across the network to the consumer. This one is stateless because you can see there's no local variables. So you can have as many of these as you want. You don't have to synchronize them. They can run as fast as you like. That's a stateless service. Because it's pretty hard to have stateless services because most of the time, you're buying a pair of shoes from Amazon, you've got to record that in the database, and now instantly you've got state. Okay. Right, there is a very important package called Java util concurrent. You don't want to have to write all of this stuff yourself by hand. So you want to use this package because it has a whole, sorry, actually I should slow. I probably go too fast. Do you have questions on statelessness or servlets? Or I could draw a diagram of a web server if you're curious. In Python, for example, they use Flask or Fast API. There's a whole sequence of these things. All right. So the Java util concurrent package, which is described in these textbooks, or sorry, no, they're not textbooks, they're recommended readings. They contain all the utilities that you need. You can also, there are plenty of tutorials online that contain that. Now, the one we are going to talk about now, well, we'll talk about thread pools and we'll talk about thread safe collections. The thread pool there was a question earlier about what do you do if you've got 1,000 threads and only 4 cores. The thread pool is the solution for that. And so we'll go right into that now. Okay. So, okay, my machine has got 4 cores. It runs quite efficiently when the number of threads is small, say 12 or something. If I get up to 10,000, then the operating system is going to spend all of its time swapping between different threads, and I'm not actually going to get much done. So as a programmer, I probably want to have control over the total number of threads that I can create. That's one of the things that the thread pool does, is you can limit the total number of threads, but it also, we do it for efficiency. The operating system controls the threads, and to create a thread, if you remember, it's got to have a stack, it's got to have the program counter, a number of things. So it takes space within the kernel code in order to do that. And creating a thread requires the operating system to do stuff. So you don't want to create threads and then just throw them away. That's sort of what we've been doing here. We create a thread, do a tiny bit of work and throw it away. So that's a lot of overhead just to run a small amount of code. So just like, I don't know whether you've come across database connection pools, but the idea is you have a pool of threads. Your program will create all the threads in that pool at the beginning, and then you'll have a class or a factory that you go and ask. If you need a thread, you go ask it. It pulls one out of its collection and gives it to you. When you're done, you release it. It goes back into the pool. And in practice, this is the way, if you've got a thread-heavy application, this is how you'll actually do it. Or as I mentioned, if you're talking to a database, you'll always have a database connection pool, because creating a connection to a database is expensive. And so you try to just have a ready pool of them. just zapped myself. Right, yeah, and the things that creating it's expensive. You've got to switch. Context switching means moving the program out of the CPU, and they take memory. Right. So the executor framework is the framework inside Java that allows you to do this. So you can create down here at the bottom, you create an object of class executor, and then you can put runnable tasks in that. And what you can do with that executor is you can limit the total number of threads in that pool so that you don't end up with too many runnable tasks. So rather, you don't end up with too many of them running at the same time. So if you're looking over here in the green, you'd have 2 thread pool. Oh, well, that one's external to the executor. You can't control your customers. They're going to slam you as fast as they can. But in order to not overload your own server, you've got a thread pool of all the consumers, so you'll never have, say, more than 10 of them running at one time, and so you don't overload. I know in later chapters in here, he talks about circuit breakers and other things about how to avoid overloading your server. Because although a web server is conceptually very simple, there's a lot of things you have to put in there so that it behaves well. Okay. So here you see we're using the executor class from Java util concurrent, and we're going to create this. In the first example, we're creating one that just has a single thread. And this one, I don't know, perhaps you might use this first one if you're dealing with some really old code that is just not thread safe. Not thread safe code means that it doesn't have any synchronized methods in there and you just cannot run it in multiple threads. And so this is code you've inherited from your grandfather, and the only thing you can do is run it in a single thread so that you won't get race conditions. So here you could set that up. This is the case I was just talking about, where you want to limit the number of threads that can be active at one time so that you don't overload your machine. And in this case, we've set it to 10. Here we're caching the threads. And then of course you can ask, how big is my pool? How many threads are queued? Sorry, how many runnable objects are queued waiting to execute? Okay, so there's an example. I want to check actually whether those are down in the sample code directory. No, we've just got the producer consumer. Yep, that's what I thought. So here we're going to create a this is a fixed size thread pool, and here's the runnable. We're using a lambda there, and we're overriding the run method, which is the important method on runnable, and it's just going to print out a hello world. Here I am. And then of course we have to be nice and shut it down at the end. So this is sort of really an architecture slide. So of course you could write your own thread pool. And in fact, in interviews, you will be asked to write your own thread pool. You'll be asked to write your own database connection pool. I know, because friends of mine have asked people for that. But in practice, you would never write your own thread pool. If you don't write one, what you'd find is inside your application logic, where you're buying shoes or whatever it is you're doing on your website, you've got all of this other code to do with making sure you don't have too many threads running at one time. And you've tuned it so that it works on a machine with, say, 40 cores, and then suddenly, I don't know, your company's running out of money, and now you're on a machine with only 20 cores, and now you've got to go back into that code and re-understand everything you've done and change it. Or worse, maybe you're spread across 2 machines, and now you've got 2 thread pools. So the point for using executor is that it brings all of those concerns of handling the thread pool into one place, and it's not put into your business logic, into your application logic. That's one point. The other point is somebody else has written it. Threading code is hard. You don't want to write it yourself. So you want to use the stuff that's in Java util concurrent. Again, like where I was at IHME, a lot of the code that did large computations, this was specifically in a programming language that is simply called R. I can write that in the first thing to do is it asks how many cores do I have on this machine, and it would only spin up as many threads as there were cores. So because if you use the executor framework, you can find out things like that, and you can also do dynamic load balancing, because you can ask, how long is the queue in the thread pool, and if it starts to get too long, you can either say, well, I better make a bigger thread pool, or you could turn off your or you could use the circuit breaker idea, which I know shows up later in the textbook, and refuse to accept more requests because you're overloaded. So your own code can reason about your load. Yeah, and so it's in the lab. And you'll be using futures, which is a callback mechanism. But let's look at some code. So a future is a delayed execution method. So here we're going to ask the executor service, and we're putting in a runnable, and there's its run method. In reality, you'd put in some big computation here, but in this case, we're just printing out a statement. And then at some future point, we can get the value from it. If we submit it as a callable, then we actually get the value. Sorry, just come back to here. The callable actually returns the value, but the future does not. It just gives you a status value, whether returned or not. So one of them is when you're trying to get the actual value. The other one is you just want to start it, and so you won't get the value back. So the difference between callables and runnables, because runnables, if you remember looking at, well, if you remember the run method is a void, which means it doesn't return anything, whereas callable does, which is why they put it in. Runnable was the original, the only thing that was callable has been added as well. And shutdown. Of course, if your program exits, the executor service will shut down, but you might want to have, this gives you the control over it. If your service is becoming overloaded, then you will want to shut it down so that it stops taking your requests. But all of the tasks that you've already got in progress will continue and finish and exit cleanly, and so that you can do a nice clean shutdown. Everybody who's buying shoes gets to buy their shoes, but you've closed the door. Like a shop, 5 o'clock comes or wherever it closes, and you don't let any more customers in, but you handle the customers who are there. And there's an await method, so you can wait until that's done. Now, Tomcat uses the executor inside to handle all these worker threads. He gets a request in, it will allocate a thread from the thread pool to your code, to your runnable, to the servlet. And then if for some reason Tomcat has to shut down, it'll use this method so that all of your threads will exit cleanly, and then it will exit cleanly the whole thing. But you normally would, unless you're writing your own server, you wouldn't use these directly. Okay. Yep. So the Java util concurrent package is very large. Off the top of my head, it's got those atomic classes that I mentioned. We used atomic integer back at the beginning. It has the execute class. It also had these thread safe collections. It has more, and we're not going to cover it all. But these ones I will cover. So the basic collection classes in Java are not thread safe, meaning that if two threads, say, update the same list at the same time, you will get a race condition and you won't know what the result of the list will be. So for example, suppose you had a linked list. If you read the length of the list, the size, add something at the end, and you write it back. Excuse me, if you had the size variable inside the list, you'd have to synchronize it, because otherwise the actual number of elements in the list and the size variable would not be in sync, because they need to be updated atomically. In database terms, you need an ACID transaction. The basic collections are not synchronized, and so it's very dangerous. So yeah, all of the original classes in Java util package are not thread safe, but you can get them. They do exist in the collections factory. The reason they're not thread safe is because they're much, much faster. And so if you're not writing threaded code, you don't have to pay the overhead of the JVM handling the monitors and handling the locks and the waits and the notifiers. So that's why the default collections are not synchronized. And if you're going to use them, the classic way is you'd create your own class and it has its own list inside it, and you'd put synchronized on the methods that update it, so you'd control access to the underlying collections. But you can, as I said, Java util collections does have classes that are synchronized. So if for some reason you only need a synchronized list, like if you wanted to implement buffer just as a synchronized list, you could do it this way. They run more slowly, but they're correct. I don't think I need to talk about Java 5.0. That's so far in the past. But yeah, the really old versions of Java don't have it. So for example, the blocking queue, first in, first out, that was the buffer example that we did in Producer Consumer. But of course, this is a generalization, so it's not just a queue of length 1. It's got multiple. The next two, are not that interesting. Concurrent map and hash map are just synchronized versions of the original. The last one is interesting, the copy on write. So this is often done in real life in production because locks, monitors are expensive. And I know people who work on some of the big systems, Amazon or Microsoft, they don't have any locks in their code. And instead they use techniques like copy on write. So if you've got a list that's shared, it's okay if you're all reading from it because you're all seeing exactly the same data. What goes wrong is when somebody writes, and then you can get into inconsistency. And the way they do it is if you're sharing data and you want to write, it will make a copy, and then you're writing to that. It doesn't have an explicit synchronization. Let's look at an example of how one of these is implemented. So hash maps. This one, we've got, say, 16 buckets, and we're going to put locks on the buckets. So the way that a bucket works is when we hash an object, we get a number. In this example, between 0 and 3. So it's a hash map with 4 buckets, and we put the lock on the bucket, and then everything that say hashes to the value 3, in this case C and B, we're just using a linear list off there. Now, you wouldn't do that. You'd have some kind of tree because lists are inefficient. But in this simple example, we're going to use a list. So these are the synchronized operations, atomic being another word for synchronized, so that we can remove or add. But the problem with that is that, it's a trade-off. So at the moment, this table has 3. If we're adding something to, say, bucket 2, or bucket 3 is a better example. If we're adding something to bucket 3, then put if absent will be called. It's synchronized. We can be certain that it'll be safe, that if 2 people try to add D at the same time, only one will add it. But if in this example, size and is empty are not synchronized, so it's possible that they will be reading a stale value of the total size of the hash map. So, but the reason we've done that is for efficiency, because if we wanted to know the size of the whole map, we'd have to put a lock over the whole map, not just on each bucket. And that would really limit the amount of concurrency. If this, say, was, suppose we're doing an e-commerce site, and these are all of the products, and these are all the orders associated with the products. If we put a lock on the whole hash map, synchronized around that, that would mean only one thread from the website could order something at one time. And that's just, the performance is no good. So instead, we're just going to put a lock individually on each bucket. So if this is, say, shoes, only one person can order shoes at one time, but other people can order socks or Ethernet cables or something. And so you get greater performance, but the risk is that the size, which is the sum over all the buckets, might be out of date. So somebody came up to me and asked about readers and writers. We'll cover what I'm about to say will be covered later, but I'm going to bring it up now because it's very interesting. There's this thing known as the CAP theorem, which shows up later in the textbook. Consistency, availability, and I think it's partitionability, which says that you can only have 2 out of 3. And so if you try to have all 3, you don't have high performance, or I think that's performance. And so what they've chosen here to do is to relax consistency so that this value will be inconsistent so they get more performance. Right. And yep. So here we're going to use a blocking queue out of the concurrency package. So we're not going to write our own. This is the example where we've got more than, so now we've got more than one message in here, and we're not writing that code. We're actually going to use it out of the Java utils package. Something I haven't talked about is this interrupted exception. You'll find that all of the methods to do with weights, anything synchronized, it's possible you'll get interrupted and you have to handle that. Typically, it's because something has gone wrong and you were waiting, and maybe the fact is that the service on the other side, all the consumers have all died, and so they've interrupted you and say, just give up. In these examples, we haven't actually filled that all out because it's not of interest. It's not the main point, but you will have to handle that. So if we set it up, producers and consumers again, and we're going to use a linked list for our blocking queue because we want FIFO behavior. Oh, I mentioned that. So this is an example of using the package. So it's simply you don't write your own code. I sort of mentioned it briefly earlier, but here's the more detail. So this copy on write array list is a thread safe variant on array list. The methods that mutate, meaning change, the array list actually create a snapshot of the underlying array. So it copies it. And then if you're if your thread is adding to the list and iterating, and the other thread is not going to see what you've added while it's iterating through it, so it stops you getting race conditions. It's useful if reads dominate writes. Most of the with concurrent programming and distributed programming, well, concurrency is a part of distribution. You're always making trade-offs based on the frequency of writes versus reads. Like if you've got a lookup table that changes very frequently, maybe you can push it out to all of the nodes that use it, and they can read it quickly. This is an example here. But if you've got something that changes frequently, you probably have to have it located centrally so that nobody gets a stale read. Yes. Yes. It's a data structure. Hash maps. So the question is, what exactly is a concurrent hash map? So you've got hash map in Java, or hash table. I've been writing Python for the last 8 years, so my Java is a little, and it is not thread safe. But concurrent one is thread safe, but it's an in-memory data structure. Does that answer your question? You don't have to write it, but if you want to use an object of that class, then you construct the object. Pardon?
The bucket you mentioned.
Yes. So let's come back to this. There's a couple of questions about this one. So let's come back. So this is a concurrent hash map. So that's the actual hash map or hash table, if you prefer. And these are the values. So when you've hashed the object that you're putting in, the hash values can only be between 0 and 3. And so you have one bucket for each possible hash value. And then if it, depending on which its hash value is, you go to that bucket and then you put it into the linked list that is behind that. And the point of this example is we put a lock around each one of these individually, but no lock around the whole table. We're doing that for performance reasons, so that we don't have to lock the whole table. The analogy is, if you've worked with databases, suppose you've got an orders table and you're getting orders from the website. If you use what's called table level locking, then if you update the orders table, then the entire table is locked, which means that all of the other threads can't order something new. All modern databases have row level locking, and so you can lock a row. If you're updating somebody's order, then all of the other threads dealing with all the other orders can go ahead. So this is an example of table locking versus row locking by analogy. Table locking would be locking the whole thing. Row is where you just lock the rows. Column lock? I know what a column. I'm not familiar with a column lock unless you're using a columnar database. Maybe you and I can talk about that later. I'm not sure, Well, you might be hashing on one column. Yeah, let's talk about that later. Yeah. So there's a lot in here. It's fundamental to software systems. It will show up all the time in distributed systems, not in the small programming like you've done in Java, but in big things. Right? Like, for example, when I was at IHME, people thought it'd be a good idea if, coming back to the example of counting tuberculosis cases across the whole world. Well, why don't, instead of having a second, we add it up for all the individual countries and then we do it once for the whole world, why don't the individual country projects also write to a world table? Well, the problem with that is they're all writing at the same time and you can get smashes. So you get race conditions or you get deadlock. So even though that wasn't programming with threads inside Java, there were separate processes running on separate machines. It's exactly the same problem that you'll see inside Java. That's why we're doing it in Java, because it'll train you for bigger systems. Solution to synchronization has many names: locks, monitors, mutex, semaphores. I think that's all the ones I can think of. Threads move through various states. I would go and look at that in a textbook because this lecture can only be a summary. The scheduler is owned by the Java virtual machine, and it's the one that makes the decisions on which thread to run. So when your code calls notify all, it's the scheduler that wakes up and selects one waiting thread to run, and it gets to hit. If you want to control it yourself, then inside the Java util concurrency package, you can use executor, and you could write your own monitors and do it all yourself. And that would be a way if you wanted to learn, or if you needed different behavior. For example, the job control system that we ran at UW, we had our own executor because we were scheduling over about 15,000 cores. Yeah, and I added the last one. Thread bugs are hard and they typically occur during production. The reason for that is production's running at a scale that even your load tests won't have tested for, and so you'll find them later, which is why you have to have monitoring. The later chapters in the textbook talk about monitoring. Production is really, in my view, the last stage of test. Your customers are still testing your code. You just didn't realize it. Okay, some more questions. Is there a question? Yep. Yeah, I think it's. Well, high performance is where you would relax consistency. So for example, in that concurrent hash map, you accept that you're occasionally going to get the wrong answer for size so that you can run faster. Now, so with availability, how much of this do I want to talk about? I'll promise that I'll check that's in the later slides. If not, I'll add it there, because availability, like a lot of systems, you'll have, say, 7 servers in the background, and they might be in 2 separate machines. Like in AWS in the labs, you've noticed there are different regions. You can have machines in US East, US West. And if you're a responsible engineer, you will spread your machines across the world so that if California has a major earthquake or something, you only lose some of your machines and the rest of them up. Now, what happens if you've got machines in California and the East Coast, and somebody in the middle of the country gets their backhoe and cuts the cable? Now the 2 machines can't talk to each other. If you get an update to the East Coast, the West Coast isn't going to hear about it. So now you've got a consistency problem if they're both running. Now, if consistency really mattered to you, like suppose you're issuing social security numbers to new people, then you might have one of them being the leader of the group, and if a server can't contact the leader, it will turn itself off. So you've now got consistency, but you've lost availability because you've said that unless I can talk to every machine, I'm not going to operate. And so that's why it's a trade-off. You just can't have all 3 at the same time. Yeah. So what I'd like to do is now, if there's no more questions, is I'd like to, if there's interest, I said about 5 or 6 slides on IP addresses, because some people ask questions about what an IP address, how they worked, what these different domains are. Now, if you've done a networking course, you definitely don't need to hear it. But as I said, there were some questions last time. So I might just find that. Because the lab one with AWS requires you to enter your IP address, and you need to understand what that is. Right. And that should be IP, not TCP. I'll fix that. So there's actually the IP, the Internet Protocol, is what it stands for. The IP address is the most visible thing that you can see. There's all sorts of layers underneath it, like Ethernet and the hardware. I'm not going to talk about that. I'm just going to talk about the IP address. There are two versions, IPv4, IPv6. I don't know what happened to IPv5. It's never talked about, so don't worry. IPv4 was the first one that really was adopted. I've never seen 1, 2, or 3. And this is the one that you will be seeing if you did lab 1 or lab 2, it's the dotted octet. So it's four bytes. So these are numbers range 0 to 255. And these are all, so it's 8 bits per number, and the whole thing is 32 bits long. And that's survived for a long time. The problem is there's only 2 to the 32 is 4 billion. There's only 4 billion possible addresses. There's 10 billion people in the world. There's probably more than 4 billion mobile phones. There's certainly more than 4 billion mobile phones and computers and Ring cameras and everything else. So there are just not enough addresses. So for that reason, IPv6 has come in, which has got 128 bits, which is 4 times, which is huge. In fact, it's so big, it's something like 1 trillion IP addresses per cubic meter of the Earth. It's difficult to understand how we'd ever run out of them. But the reason it's so large is so that you can do bit masking and create subnets. So I'm not going to go into that. But we will always have sufficient IPv6 numbers. But it's been slow adoption. You know, I think, I'm trying to remember when I first heard about it, 2010 or earlier, but you'll still find that not everything supports IPv6. The last time I looked, about 30% of the traffic on the internet was this, but not all of it. We're not going to talk about it, but I mention it so you know it, because you won't see it in AWS. Okay. Every IP address on the internet must be unique. So when you take your laptop and you connect to a website, that website has a unique number. No other machine in the world has it on the internet. I'll emphasize that in a minute. And your laptop has a unique number on the internet. And there is an organization called IANA that manages that. The way that works is that each country is allocated a block of numbers. And then within that, your ISP will be allocated the block of numbers, the university is allocated the block of numbers, and they can't go outside that space. But there's an escape. This is what I was talking about before. I talked about last week. There are two ranges of numbers that are called, which are private. These ranges will never be allocated to a machine on the internet, and so you can safely use it inside your own network, because as long as you don't let that number leak outside to the external internet. And there's 2 of them. There's the 192.168, and it has that range, 192.168.0.0, all the way up to 255. Sometimes written like that. In the AWS interface, it's written like this. That's called CIDR syntax. And what that is it's it's telling you that the first 16 bits, and these are 8 bits long, so 8 plus 8 is 16. The first 16 bits are fixed, and the next 16 are free. So the number refers to the number that are fixed. So in this case, the first 8 bits are free, and after that, all of them are now. Sorry, the first 8 are the first octet is fixed, and the next 24 are free. So internally, like within your house, if you run a home network, you'll be using 192.168 numbers or 10s. I will gloss over how it works to the public internet. Just a question, is this all familiar to all of you, or was it only one person who didn't know? Okay, I'm getting good. So there's two things, machine. The IP address identifies the machine, and when I say machine, I mean actual physical machine like this laptop, or possibly a virtual machine. Okay. And then the port identifies the service, the software service within that machine. And each software service or daemon, there are well-known meaning standardized by custom and usage for certain things. The SSH daemon, which when you do lab 1, you'll see is always 22. HTTP is always 80. 443 is HTTPS. 8080 is the Tomcat default. When you bring up a Tomcat server, even though it's a web server, it doesn't actually listen on 80. The reason for that is because Tomcat's often used for testing, and so you bring it up on 8080, and only when you're certain of it do you put it onto 80. Here we go. So let's suppose we've got a server, a client and a server, and the client's address, this is within your house, 192.168.110, and then the server's on 192.168.1.20. So 2 machines, 2 IP addresses. And we're going to try to do an SSH from the client to the server. This client's a Windows machine, so we're using PuTTY. If it was a Mac OS, we'd actually just use SSH. And so the blue, it's going to send a message, 192.168.1.20, onto port 20. The syntax is you put a colon in the middle to separate the IP address from the port. When it hits the server, the operating system sees the port number. Yep, got it all written down. Yeah, the operating system receives the message. It has a table linking the daemons, the software services, to the port number. And it knows that 22 is this daemon, and so it routes that message internally. And whatever it is, perhaps you send an ls command across. This program executes, it gets some results, it needs to send it back. And so the message goes back to 120. I forgot to mention that. So there has to be a port here. When you initiate the conversation, the operating system will give you dynamically a port for your conversation. You don't have to specify. This is all well below the level you're programming. You will not be doing socket programming in this course. Socket programming is also hard, but I wanted you to understand how IP addresses work. So you send to an address and a socket, and then the response comes back to your IP address. And I've got a typo here, that 20 shouldn't be there, and a socket that the operating system has created for you. So that's what we've been doing with AWS. Another little bit. So I'm sitting on top of that, because you don't use IP addresses. When you go to a website, you don't use the IP address. You actually use a name, such as northeastern.edu. And there is a whole worldwide system known as the Domain Name System, DNS, that maps names to IP addresses. You can just think of it as a giant global hash map. It's highly concurrent, as you would imagine. It's highly distributed, and you can access it by NS lookup. I could show you some stuff to do with that. There's a lot I could talk about, but I'm not. VPNs or NATing, because inside your own house or inside Amazon's network or Microsoft's network, they're using the 10 dot series. They have a thing called a NATA, network address translation, which takes the private numbers and matches them to one of the numbers that company's actually been allocated, sends it out. But I don't want to go into details of that because this is just 7 slides. This course will tell you far more. The 5700 covers that, but it covers all the layers below it as well. So that's what an IP address is. Just fundamentally, it's a unique identifier for a machine, whether it's a machine or a physical machine or a virtual machine, and the port number will connect to a certain service within it. Oh yeah, actually, another use of VPNs. Okay, well, that's what I had for the lecture today. There's 20 minutes left. These ones I try and remember. I will upload these ones, definitely. Is there more you'd like to know about networking? Like what how NATing works? Yeah. Actually, I've got a little bit of time. So let me talk about NATing. Network address translation. So if I'm sitting in here, let's see. I'm sorry, I'm just gone quiet while I read this stuff. And I'm going to change glasses so I can actually read it. Okay, so you have a look here, this bit. So Ian, so this is Mac OS. Is that too small or can you read it? Okay, EN0 is my Ethernet 0 port. This is actually a hardware address. Not going to talk about that. And you can see there is a 10 series number that's been allocated by Northeastern EDU, Northeastern Tech Support. So that's my number inside Northeastern, but it's not the number that I'm known to the outside. And you can see I've actually got an IPv6 number. Now, can I zoom in? I actually don't know whether I can zoom in. Yes, I can, but it's not called Zoom, it's called Bigger. I'm looking for EN0, there it is. So there you can see I've got a private number, and that would have been allocated by Northeastern Tech. And what I want to show you now, there are a number of sites that do it, but how do you know what is my IP? Well, there is a website. To the outside world, this is what I'm known at, is 63.208.114. That's my external number. So there is a server that Northeastern's running that's doing network address translation. And it's basically a big lookup table between this external number and its internal network numbers. So when it gets traffic back from Amazon to this number, it knows internally to send it to my laptop on this number. Now, none of this IP address stuff is going to be in quizzes or anything. The reason I'm doing it is because in order to do the labs, I think you need to understand a little bit more about networking. But we didn't want to require 5700 as a prereq because that's got far more than you need to know in order to succeed in this class. Okay, well, that's all I actually wanted to cover today. I can go through, actually, I do want to talk about what the reading is and things like that. Let's get rid of that. Because that's one of those places that's going to thrash my CPU. All right. Difference between thread and a process. Well, the process has one address space. It has its own address space. The thread, all the threads within a process share it. So this is the mandatory reading. As I said, you can get that through O'Reilly. The optional reading, I really suggest if you're interested in, that you really do look at it. This is an O'Reilly? No, this is a PDF that I've uploaded. So you've got it there. There are various others books you can get. There are also good tutorials that you can find online. There's two parts to the lab. Okay, the first part is concurrent programming, so it'll be much like what we've talked about. The second part is all about using servlets, which we didn't cover, which this lecture doesn't cover so much. It's well, let's talk about the first part. Here you can see this is the Java part of it. So you're using the stuff we've had talked about in the lecture. And the emphasis here is to do a bit of experimentation and to look at the performance you're getting and the performance degradation you get when you're doing synchronization. Yeah, that's what it's all about. But it's concurrent programming is how it's good to do this. The second part is about using Java servlets, and it extends the first AWS lab. Now, I suspect a lot of you haven't done that yet. I know some of you didn't have invitations. It was fiddly getting it to work. It's tricky. You won't have all set it up, but you need to get working on that very soon because the assignment includes first assignment and builds on it. So here we're doing, you can see servlet programming, but they've got a lot of examples here of how to do it. Unfortunately, it's all in XML rather than JSON. So that's a lab. So we've got about 15 minutes left. I just need to take a break and then I'll be next door. If you've got problems with the lab, I know the Jay-Wei, the TA for this course, took this course last year, so she's quite experienced with the AWS. I can also answer, basic questions. I can show you what I've done. The risk of me debugging in front of you is it's probably not going to work immediately in front of you. But the lecture for today is over. As you can see, this lecture has a lot more than the last one. In fact, if I teach this again summer, I'm probably going to toss that first lecture and put in a whole lecture on containers and Kubernetes. Because the AWS, we're using EC2, Elastic Cloud Computing. It uses virtual machines, but that's not the only way that people do distributed computing. Everything I did at the university was using Kubernetes and containers. And I think you need to know about that as well. I've got to work out whether I can fit that in somehow. Okay, run away.
If Ronald like said to you that he wants to do it with you, you should let him know like you will do it. Oh, okay, yes. Because yes, you know about it, so I was just not sure it's going to register.
Well, the virtual machine probably. You see that.
有艺术人
那不是就不是用不用教的，自己做，我觉得帮助你了解怎么。
对对对，他就4个 assignment。
但是我也没有就说要。在4个作业之后还是。
对对对，他们还有。我其实不是这个 section， 我是中午 section，因为他们好像先5个一样。4个 assignment， 然后final project。
中午的那个老师讲。
那个就是那个老师讲了。
会更有经验。
有运有，不是正好周末有事儿，所以我来听看这个。那个老师讲的也不错，
也还可以，
挺好挺好。
那节周五的那节课人会
很多，比那节课人多，因为那个老师讲了很久，而且他本身就是 Amazon 总部的一个 L6嘛，所以他就会讲，他就会说很有用啊，他就会给他讲一些你们以后这边都会用到的一块啊。
挺好。对对。
特别急，那是这样。那这边打算怎么办？感觉还是没有吹就很难。没有吹就都不想上早班，老师也讲不清楚。下去吧。
哦，那谢谢具体。呀，是不是就是说，scientific research？
反正那个网站我打不开。
他 lab 里面写了一个东西呗，你要不放 ？Where is the hypothesis? You know, that's yeah. Yeah, to talk about that. I didn't think that much. But like,
I was like logging, I was dying. Then I got like almost to go and get. That's why you have to get the. Yeah. He was just too soon. It should be faster.
Chips and
just I think like an actually straight administrator. He was serious. He was like, no, you gotta go. I tried to like circumvent this situation.
Some people like trying to get on campus without an ID card.
I said I'm this guy. I said I'm gonna go just after this class. And I feel like slicing Tamil into 7 cookies.
现在有的 base 里面，我不是在这个
Like a bunch of vegetable.
It's like salt or sandwiches. I haven't tried this.
Say
The
the.
instruction to me. That wasn't the way when I used to use Tomcat. That's not about round trip. What I'm using.
What are they going to do?
It is.
No, the already expired.
Yeah, because I've noticed that you can stop Tomcat and restart it.
对对对，那个是方便。
Just know that I have lost you. Just know that I have lost you. I am. Well, black up my steps. But like, you don't need fish or birds, like chicken or something like that. Why? Like, I understand the big animals like that, like brains are much more formed.
So yeah, if you, you could choose not to do it, you could choose to do it late. But good idea, especially, let me just,
是。
Real life, I know, so point, I don't know about the morality of killing. Have universal standards?
我记得我用过它。
而且最后口罩也差不多，就没有必要摘。那他把你和不是的。
哎，我们要把这个放在纸在哪儿吗？还是
都可以，你们要是回来的话，
你用过那个锁吗？回来，
我回来，我也回来，那我也回来吧。
没用过啥。我记得他那里好像有一个可以锁，
可以锁的2楼好像。看看先。
就是我好久都没有见到。怎么来学校的？啊，是的。我给你看的。把人上的。
I will take off his mouth. Oh, that's really funny. I don't know. Maybe that's like. Boxing. He does MMA. That's why you're watching it, yeah. Is that a lot of like gangsters and like? I have heard about like, yeah, I have heard about like Nigerian like gangsters. Never about it.
yes, that's the case.
Not much fighting.
Yeah, absolutely. So that's why I put it as a section of my picture.
Just well tried.
Because the
trainer once.
The three.
Or a couple of times, but not.
Where
Not. There is this country where like you have different shades of brown black people.
Yeah. There's an option.
Like there's an African country I heard like has very like vibrant shades.
I actually went off and used that.
I'm not sure like whether it was Ethiopia. I saw like some other country.
I know there's same stuff every year. Yeah, probably it's different, some South American countries, something like that. I think like Brazil or something.
Yeah, there was,
They have a huge range.
hey. Hi.
Look,
I was actually planning to be both of you.
So here we are.
Isn't there
There a library you can load up.
Maybe there's a library even. Make sure you keep the second one.
Yeah. There is management system tomorrow 6:30.
I
6:30
moved
to
to leave it.
6:30 to 10. 6:30 to 9:15. What about yours?
To,
No. What is it?
okay, yeah. I was like, first class, they dove directly into the content, so it's,
Would you say like
David Snowfall.
compared to
I
this?
heard, yeah, that was tough.
Is he?
I heard, no, I mean, the course is at least like.
Oh, the
heavy.
courses, yeah.
You think algorithms or advanced algorithms?
Right now.
Yeah, advanced algorithms or algorithms.
Regular, there's like requirements to graduate with it.
I've decided like I'm next semester to take information retrieval. The course are flexible. Or which courses are taking?
Information retrieval.
It's like for that. We're doing like data science, or do you want to just
Next year, spring.
Computer vision. But I really take.
well, I'm gonna take a course on summer. I can take one course, I guess.
Yeah.
你是自己做吗？带一下，带一下。我刚下去晚上的，我看你要回国了。
I generally prefer not to.
你们回去有1个月？
Then like stand
没有啊，回去2个礼拜，
and then
是我订过最短。有的还没回来，有的还没回来，我有订到还没。你在晚上？你在吃饭？我问一下我看。
It's quite clear. That's the IP, that's the DNS line of the server, which now, that's actually its IPv4. Because it will be translated internally Amazon, use its own private network. So I then attempt to, that's them. Here I attempt to SSH. Why did it fail? Because I forgot. Need to include the certificate. Yes. Cross my fingers. Okay, so I've got an issue. Yeah. And this is fairly securities. The thing with securities is if there's a mistake, it has to be the same name. That's really the way to debug. It's possible I have to reboot, actually reboot the instance. I have to look at why, because when I look at it, that's the same key used to create. So I'm not sure. Oh wait, if you were talking about it.
What's up? Because I found that I found the code. Yeah, slow eyes.
You don't call me out code if it's important.
Yeah. But I have another question, like, you mentioned the flashes.
Yes.
So do we need to choose when we apply the thread? Like the
Yeah,
thread?
if you're using threads, you would need to use a thread safe collection. Or you would put the collection inside your own class and put synchronized methods. Your name is one person. Your diction?
Diction.
Yeah. Mhm.
Visiting there and looking around to see what types of student activities are currently going on and notice that a lot of students have a passion for building full stack apps.
Yes.
Not necessarily full stack, but software that is finished and that can be put out there in the world for anyone to use.
And still on the resume.
Yes, that too. That's definitely one of the reasons they're pursuing it. Because leak code is obviously number one, but I think that much more interesting and much more functional, better learning experiences for people to start stuff, right?
Yes.
So we're putting together the club to do precisely that. And we have a series of seminars on different topics, including front end, back end, and also some on product and trying to understand people's needs in order to come up with products that actually solve problems. I think that a big part of it is understanding how the systems that are scalable.
Okay, yeah, no, I can do that. What exactly?
So one of the benefits of the club is that we have a list of experts that students can reach out to for specific topics. So we have experts on low-level programming, on front end, and hopefully on distributed systems. So kind of featuring you on our website.
Oh, yeah, no, you can
as a point of contact.
Yeah, because particularly I'd like to talk to each group before they decide on the technology. Yeah, UW are also using Python Flask, doing Fast API, using the web server.
That's API.
Fast API.
Met the person who wrote it.
Oh,
He's from Colombia, from my home city.
Oh, Colombia, not Colombia. That's in the country. Yeah.
Correct.
Yeah, okay. Yeah, we had one guy out in my fourth grade. My team. Yeah, so that would be.
Makes sense. I mean, we have a variety of projects. For instance, I was building one that is on track. And the stack for that one is like the Merge stack. I use TypeScript on both the front end and the back end. And then there's another student that has a project that's fully built on Rust. And he's building an email server. But I agree that like if there is a kind of best standard for kind of putting out a blueprint of how to build it. We were going to go for like the MERN stack and having JavaScript on both sides.
Well, you can do that. I personally am not a JavaScript programmer, which is why I would.
That works too, but if maybe Python is better, we can perhaps consider doing the blueprint to follow that.
So we were thinking of, our entire club consists of 2 parts. One would be the online, one would be the offline one. The resources we will provide online to our website would be few blueprints. I was thinking of having few blueprints on, depending on their use case, they can pick up one, and that can also have a discussion forum where they can discuss, okay, I was trying this tech stack, but I found this better, or these are the challenges I'm facing. Along with that, we will have some experts there where we would like to mention you as well as an expert, so they can reach out to you and get together. In the offline session, we want to have certain seminars where we can bring industry experts or someone from our college itself, like students or faculty, whoever is interested in and can give a seminar on any topic. So that will be topic wise, so we can integrate calendars. So if you are going to like something, you can go to the calendar from there and just go through the seminars of each topic.
So by blueprints, we mean we kind of have like a syllabus, and then throughout a semester we give certain chats, and then on the calendar you can see when the front end one, when the back end one is, and so on and so forth. So you don't have to go out to all of them. You can go to the ones where you're stuck. The other thing that we want to support students with is kind of promoting their products. So in kind of the full stack spirit, creating a web page for them to talk about what they've built and what that looks like, and kind of have that professional looking place for.
Yeah, okay, no, I can certainly, I can provide advice, but I can't debug. I have to limit the amount of time I spend. So I'm not going to be debugging people's systems.
Yeah.
So I would be able to give an overview of what I choices for technology.
someone is stuck with your project, we'll arrange a weekend seminar or something.
A hackathon kind of thing, but
Yes.
it's
But
like
like-
everyone sits and
Yeah,
works on it.
everyone can come together among students and we can just suggest where they are stuck, we can debug together.
Yeah.
So that was the idea for it. And so I think there are two places where you can pitch in. One is advising, like being an expert in the website, and another is like if there comes a request of understanding more on the tech stack or giving like they need all the students need some overview, then probably you can take one seminar on that topic.
Yeah, I could do that. No, I can't do it. I've got.
Once per semester or
Yeah,
something.
it'd have to be March.
That works. We can definitely work around your schedule. Awesome.
Good, thank you.
And then, yeah,
How many
I'll-
people do you have so far?
like eight, not too many. We
Yeah.
just started.
Yeah.
But it's very casual, and it's kind of like whenever people can give time to this club, they'll do it. But we understand everyone's really busy and doing.
Yeah, they got their day jobs to do.
Yeah. Thank you, Professor.
Thank you.
So Professor, can we have you in the mail chain of?
You can put me in.
Okay,
Yeah, so use my.
sure. And if you have any feedback at any point of time, you think something we can do differently or something we should add, please let us know.
We'll have our kickoff event next Wednesday at 4 p.m. in the 310 building.
Okay.
We'll send you a mail.
Yeah, thank you. Yeah.